Welcome. We want to take a look at an example of sketching a rational function. This will walk through finding all the appropriate pieces and then ending with us sketching the graph. Our rational function is given here, and it is already factored. Similar to what we had done before, we'll go ahead and cancel common factors in the numerator and denominator, like x minus 2. And it looks like that is the only common factor. Since it does eliminate the x minus 2's completely, we need that this equality holds for x not equal to 2. Okay, excellent. That also helps us understand where we're going to end up with those holes in the graph, right? Whatever numbers we list here, those x values, associated x values, will be those of the holes in the graph. So let's get the zeros of the function. The function itself is equal to 0 when the numerator of the rational expression is equal to 0. That numerator is already factored. So we're going to get 0. So when x is not equal to 2, so I don't need to worry about this factor, because if I said x minus 2 is equal to 0, x equals 2, x is not equal to 2. Okay, that's not a 0. So we don't really need to worry about it. It's written here for now. That's okay. We have x plus 4 is equal to 0, so x is going to be equal to negative 4. We have x minus 1 equal to 0, so x is going to be equal to 1. And we have x plus 1 equal to 0, so x will be negative 1. So we have 1, 2, 3 zeros of the function. Again, when we have a rational function, it will be equal to 0 precisely when the numerator is equal to 0. We use the zero product property to set each of the 4 factors equal to 0. X cannot be 2 because we have division by that. We would have division by 0 in the original expression. And then the remaining 3 factors do give us zeros. So locations for x-intercepts. All right, we want to now identify the location of any holes in the graph, which can be done when for x equals 2. So when x is equal to 2, we get a y value of, we plug it into the simplified form, but that simplified form contains a factor of x minus 2 in the numerator. X minus 2 is 0, so it immediately gives us 0. We'll write this out just to be clear on how we did it. So 2 minus 2 gives us the 0. 2 plus 4, 2 minus 1, 2 plus 1, divided by 2 plus 2 squared times 2 minus 3. Now, I know that's going to be 0 because this thing here is 0, giving us a numerator of 0 and an overall value of 0. So there is a hole at 2, 0. Now that makes sense because we expected it to be a 0, or we wanted it to be, but it's not because we can't plug it in. So we get a hole at that location instead of 0. All right, we want to identify the vertical asymptotes of the graph if there are any. The vertical asymptotes are identified by the factors that remain. So factor of x plus 2, asymptote occurs when there's division by 0. So x equals negative 2 is one vertical asymptote, and x minus 3 equal to 0. Again, vertical asymptotes when there's division by 0. So x equals 3 is another vertical asymptote. Next, we want to identify the horizontal or slant asymptote, if there is one. And if it is a horizontal asymptote, we will identify where it crosses. All right, we have a degree 5 over degree 4. So there's going to be a slant asymptote. So 5 equals 4 plus 1. So we have a slant asymptote. Now we can identify that by performing the polynomial division. What we have as our divisor is x to the 4th minus x cubed minus 10x squared plus 4x plus 24. And the thing we are dividing is x to the fifth, plus 0x to the fourth, minus 13x cubed, plus 16x squared, plus 12x, minus 16. Excellent. So this is our divisor, and this is what we are dividing. So let's see here, make the coefficients match of the highest degree. So I need to multiply by just x to get x to the fifth. So we'll have a minus x to the fourth minus 10x cubed plus 4x squared plus 24 x. There we go. Perform the subtraction here. X to the fifth minus x to the fifth gets rid of the x to the fifths. Wonderful. 0 minus a negative 1 is a positive 1, x to the fourth. Negative 13 plus 10 is a negative 3. 16 minus 4 is 12. 12 minus 24 is a negative 12. And we still have the negative 16 here. Now to get the coefficients to match, I just need to multiply by 1. So I'm going to have x to the fourth minus x cubed minus 10x squared plus 4x plus 24. I really don't need to perform all of this. This already tells me what that slant asymptote is, but it's nice to write it all out. So x to the fourth minus x to the fourth gets rid of the x to the fourths. Negative 3 plus 1 is a negative 2. 12 plus 10 is 22. Negative 12 minus 4 is a negative 16. Negative 16 minus 24 gives us a negative 40. So we can write our function r of x as x plus 1, that's our slant asymptote, plus negative 2x cubed plus 22x squared minus 16x minus 40 divided by x to the fourth minus x cubed minus 10x squared plus 4x plus 24. And the slant asymptote is given by y equals x plus 1. Excellent. Now we want to use those various parts to tell us what the graph of the function is going to look like. So let's return back up here and we'll transfer these pieces over one at a time. So we have these zeros of the function, negative 4, negative 1, 1. Negative 4, negative 1, 1. Those are the zeros of the function. We'll go back to the previous page to identify what is next. Location of holes in the graph. So there's a hole at 2, 0. Let's go back to the graph. At 2, 0, there is a hole. Previous page again. We're going to plot the vertical asymptotes. So there is a vertical asymptote at x equals negative 2 and x equals 3. Negative 2 and 3. Negative 2 and 3. Get those drawn. Excellent. So I have most of the information at this point. Let's go back and grab onto that slant asymptote. So we have slant asymptote of x plus 1. Y equals x plus 1, so it's going to pass through here. looks something like this. That looks pretty good. So we have all of these pieces of information. Very interesting. Very interesting. All right. Now what we need to do is we need to figure out where things lie. So using some test points would probably be a good idea. So I could plug things in like -3, for example. Let's see here. There's a 0 here and a 0 here. Yep. All right. All right. Okay. So this gives us a pretty good idea of what's going to happen here. If I were to plug in R of -3, this will pretty much tell us everything that we need to know. I'm going to go back and use this particular representation, R of -3. So I'm going to use this one here. We can use the simplified version, that's fine. So I have -3 minus 2 times -3 plus 4 times -3 minus 1 times -3 plus 1 divided by -3 plus 2 squared, -3 minus 3. All right, so -3 minus 2 is 5. -3 plus 4 is 1. -3 minus 1 is a -4. -3 plus 1 is a -2. -3 plus 2 is a -1 squared, would just give us 1. -3 minus 3 is a -6. There is a common factor here of 2 and 2. I have 2 negatives and 1 negative here, so these ones will cancel. That leaves me with a -3 in the denominator. This is gone. 5 times 4 is 20. If I wanted to, I can observe this as, let's see here, 20 divided by 3 would be 6 2/3. If I wanted to think of it that way, so I could call it approximately 6.67, and that would be all right, negative. So at -3, it's about negative, or it is -6 2/3. So it's going to be way down here somewhere. Oh, that's no good. I don't like that very much. See if I made an error somewhere. -3 minus 2 is a -5. I missed that negative. There we go with those negatives again. So we'll end up with a couple of negatives that cancel out. Excellent. 6.67. That looks better. So that would be up here somewhere. Okay. This tells us pretty much everything that we need to know. Since this is a vertical asymptote, I know that this is going to go like this. But I also know that there are 2 factors of x plus 2 in the denominator. So this gets us what we call an even vertical asymptote. So it will point in the same direction. Come down like this, and it has to cross the axis here. Now, I don't care too much what this looks like. I just know that it's going to come back and cross the x-axis here. And again, here it will cross again, and we have a vertical asymptote that goes down. And now you might ask yourself, well, Dr. Reynhout, don't we need to test a point over here to figure out if it's below or above? Well, no, just like an even vertical asymptote, they both go to positive infinity on each side. This one was an odd vertical asymptote, so I know that it's going to come down, and then now it's going to become tangent to that oblique or slant asymptote. So this is what the graph of our function should look like, approximately. Now, where I am passing through these x-intercepts here, that is also can be identified as we did for polynomials. Those zeros were identified, right? This has a multiplicity of 1, multiplicity of 1, multiplicity of 1. So each of those, it just simply passes through the axis. So we have the ability to sketch that. Now, if we wanted to, if you were unsure about that idea of the even and odd vertical asymptote, what I would encourage you to do is I would encourage you to evaluate at points like -3/2. Right here maybe, and you could evaluate at, let's see here, 5/2 to see what's happening here. And then you could evaluate here at 7/2 to observe where that value is. But that tells us everything that we need to know, and we should be all set.